Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture we talked about the idea of photonic band gaps, and in this lecture we want to take the discussion forward. Before I get into that, let me see if there are any questions. Yeah. Alright, so in the live audience here I have a student who is asking, so he knows about the electronic band gaps and he's asking me how can he compare that with the photonic band gaps. So he understands what an electronic band gap means. So in essence, the photonic band gap is very similar to an electronic band gap. It's just that if you have an electronic band gap, you can't excite an electron hole pair at that energy, right? Within the band gap, you cannot have a state available. So photonic band gap means within the band gap, you don't have any electromagnetic states available. So if you actually try to shine, let's say a photon in that energy, it will not propagate through the material. Okay, that's what a band gap essentially means. So maybe, the discussion in this slide now today, what I'm planning to do, that will help clarify this question. So let's see. So this is where we left off in the last week. We talked about the gallium arsenide and air multi-layer stack. We said that effectively you have this band gap that opens up, and the extent of the band gap, that is, the delta omega by omega, is essentially the mid gap to the band gap to the mid gap ratio, right? That we said is proportional to or equal to delta epsilon by epsilon, and there was a sign term, I think it was pi d by a, right? Pi d by a divided by pi. This is what we said was the expression. Okay. So now I did not clarify this a little bit, so I think I should. So this in the discussion, gallium arsenide air multilayer, gallium arsenide has a permittivity of 13, we said epsilon equal to 13, and then air has a permittivity of epsilon 1. Okay. And we looked at the picture also last time and we analyzed this. So we said here delta omega is basically 0.15 to 0.25. So this is 0.1 delta omega divided by the mid gap frequency is 0.2. And we said that ratio was about 1 by 2, so 0.5. Okay. But we didn't verify whether this expression that we have here in the bottom is giving that. So let's try to compare. Okay. So in this case, delta epsilon is basically the difference in epsilon of the layer. So 13 minus 1, I would say that is 12 divided by the actual epsilon, let's say is 13, the high index mediums, into sine of pi d by a. We said in this case, this is simply a multi-layer stack wherein the one is high index, one is low index, both have equal thicknesses. So basically the width is d, the periodicity is a of the stack. So the d by a is essentially 1/2, right? So this is into 0.5, that is write it as pi by 2 divided by pi. Okay. So I can see that it roughly translates to 1 over pi. So 1 over pi will be roughly 0.31 something. Okay. So you see that the expression that you use is giving you only this band gap to mid gap ratio of about 0.3, whereas in this picture, in the band gap that's calculated with the exact numerical calculation, you see that it's about 0.5. The reason that difference came about was this expression, while it's it's useful to understand the concept that whenever you have the index contrast to be high or the epsilon contrast to be large, the band gap will be large. That's what I wanted to communicate through this expression. But this is still what is known as, a perturbation based on perturbation theory. That means we're assuming that the perturbation in the energy. So if you have an epsilon, the first case that we considered in the last lecture, wherein, we talked about this particular case, wherein there are two layers, epsilon 13 and epsilon 12. When you have such a scenario, we can consider the change in the epsilon as a small perturbation compared to the background. The background could be 13. And in this case, the epsilon is 12. So basically the delta epsilon is -1. And so the perturbation is only small compared to 13. 1 compared to 13 is very small. So in this scenario, this expression will hold very correctly. All right. So for example, here, this would be, delta epsilon is 1 divided by 13 into sine of pi by 2 again. and divided by pi. So in this case, you will see that the answer is quite close. Okay, it will be roughly about 2% or something like that, 0.02 or something like that, right? So in this case, this would be correct. But in the example that I've shown on this particular slide, wherein the contrast is large, one epsilon is 1 and the other one is 13. In that scenario, this expression will not be very accurate. So if you have to deal with this situation, we'll have to do exact numerical calculations. Okay. So there is, you can actually have software which solve for the eigenmodes and so on, which I don't think you need at this stage. So you can actually figure out about the band gap by calculating the reflection transmission also. So in the first lecture of the week, I introduced the T matrix approach, wherein we calculated the transmission and reflection spectrum for multi-layer stacks. So if I put in this epsilon of, let's say, 13 and epsilon of 1, and then I put in the T matrix code and I calculate the reflection. So the output is what is shown on the right here. So on the y-axis, you see the reflection, and the x-axis, we see the normalized frequency. So I have taken the taken the constants, the lattice constant and the wavelength and so on, such that I get this normalized frequency. So in fact, I'll actually put this code on GitHub. I'll also give you a brief demo of this so that you can know how to use this. So essentially what you see now is, for the normalized frequency between 0.15 to roughly 0.25, you see the reflection is very high. The reason this happens is, when you take a stack containing this, you see the band gap is roughly from 0.15 to 0.25. So whenever there is a band gap, that particular photon or that particular wavelength is getting reflected. It is not propagating in the medium. It cannot support. That's all it means. All right. Similarly, an electronic wave, if it has a particular k vector and a particular energy, there is a certain band of energies where the electronic waves cannot exist in the electronic material. That's why we call it a band gap. You can have a state below the band gap or above the band gap, but not within the band gap. Similarly, here photonic waves, that is electromagnetic waves of a particular energy and k, cannot exist. If you look at this, there is no k for which there is an allowed state. The allowed state is denoted by this line, right? The blue lines here. So the lines are not present in this, so we call it as a band gap. And whenever the band gap exists, we get a large reflection. All right. So this is how you can actually analyze the band gap. I mean, if you don't know how to calculate the exact, using the eigenmode analysis, if you don't know how to calculate the band structure, it's all right. We can use a simple T matrix theory that we have learned so far and calculate the, we can actually look at how the band gaps occur. Okay. All right. So let me take one step forward. How do I design the band gaps? So far, I have given you some examples wherein, the epsilon was 1 and 13 or, 12 and 13 and so on. But how do we design? I want to change my band gap. I don't want it to work at this. I want it to be at a certain different wavelength, let's say. So in this case, when I say this is, 0.3, right, in the y-axis, let's say we said it is normalized frequency. A by lambda is, let's say, now let's take the mid gap. So that is 0.2. So in this case, let's say I'm taking a lattice constant of A equal to 500 nanometers. Just for example, if I take, where does my band gap, band gap occurs at lambda equal to 500 nanometers divided by 0.2, right? So that will roughly translate to what, 2500, 2.5 microns. So if I want it to occur at, let's say, 500 nanometers band gap, I have to choose the lattice constant to be 100 nanometers and so on. All right. So you see the trend. You can even see the trend here that we previously discussed. So for example, let me move it here. So let me rewrite this so that it makes it slightly easier. I'll say that, let's consider A by lambda equal to 0.2. Okay, that is the mid gap, right? So how the normalized frequency or wavelengths help us? So now let me choose a lattice constant of A, and then this is lambda bg, right? Okay, band gap, I'll say. So if my A was 500 nanometers, immediately we'll say that the lambda band gap is 2.5 micrometers. Okay, so I have to get to 100 nanometers periodicity to get a lambda band gap of 500 nanometers. So if I create a stack containing gallium arsenide and, so for example, gallium arsenide and air. Okay, and this periodicity is 100 nanometers. If I create such a structure, then I will see that my band gap is going to be at 500 nanometers. So it will perfectly reflect 500 nanometer light. That is the meaning of this graph, right? So if I increase the size, of course, it's going to reflect at longer wavelengths. That's it. All right. This is assuming that the band gap is, the epsilon is actually constant all through, which is not going to be true. So if you actually deal with real materials, you have to put in the epsilon and real and imaginary part for the real materials, and you'll be able to do an exact calculation, because we know how two matrix works. So we use this as a starting point, and we assume that it's a dielectric. So, it can work. But if you actually think about it and understand deeply about the material properties, gallium arsenide has an electronic band gap at 870 nanometers. Okay, so any wavelength below 870 nanometers is going to be absorbed by gallium arsenide. Okay, so even if you try to use gallium arsenide and get a photonic band gap at let's say 500 nanometers, it's not going to work, because it will get absorbed electronically, right? So it will simply, it will not reflect, but it will get absorbed. So in effect, if you want to really create a photonic crystal, which is an analog of an electronic crystal, you'll have to make sure that the photonic and the electronic band gaps also coincide. I mean, the photonic band gap has to be within the electronic band gap, right? Otherwise, there are issues, okay? Especially for emission that can occur through near the surface. All right. Anyway, all right. So I hope this clarifies the question a little bit. So now let us think about how to actually design these structures, photonic band gaps. So far, we are given something, right? The way we can design is, we mentioned this, we said that this is a stack, right? Multi-layer stack. So one of the simplest things I can do is I can change my thickness of the index medium. Like for example, I'll take now the same periodicity of, let's say, A, but I'll change the thickness of my constituent layers. For example, this is gallium arsenide. Okay, this is gallium arsenide. Now I'll choose thickness to be D of 0.2A. Okay, so the periodicity is A. So my thickness of the structure is going to be 0.2A. And then the air region, which is in between here, let's say I'll choose this. This is air. And I'll choose this to be thickness of D equal to 0.8A. I can choose that, right? That's what I have written here anyway. So if I choose such a structure, I'll see this is a very easy thing to do. The thickness of the constituent layers can be easily modified, and we can compute the band gap again. And that is what is shown here. Okay. Now you see that now we are on the y-axis, we are going from 0 to 1. Okay. In the previous case, we were only going from 0 to 0.3. Now we are trying to take more frequencies into account, normalized frequencies, and x-axis is the k vector. You see that there is for the first photonic band gap, and then there's a higher band gaps as well. So this is again beautifully matches what we know from electronics, that the band gap is not, there's not single band gap. Generally, whatever we use as band gap is the lowest band gap, that is the peak of the valence band and the minimum of the conduction band. The difference is the band gap. But then if you go to higher energies, even in electronic materials, we see that we have other higher band gaps. All right. So this is not just the so you see this first band gap, second band gap, and so on. And we don't need to take this for granted. We already have the T-matrix code, which we have developed in the previous, I'll share this again with you, wherein you will see that if I reduce my thickness to 0.2, previously it was 0.5A and 0.5A, both the gallium arsenide air structures were actually having the same thicknesses. If I do that, I got the previous spectrum. Now I just change this number. I can immediately see that the reflection spectrum is now exhibiting a beautiful trend like this, wherein you see that here, this is basically between 0.2 and 0.4, the reflection is maximum, indicating that, roughly slightly more than 0.4 actually. You see that, and here the band gap, it's exactly matching the band gap here. And again, similarly, if you look at anything above 0.85 or so here, you see that this region again exhibits a reflection, and that's what you see here. And in between, there is a very small narrow region, small band gap. And because it's a small band gap, beautifully you see that the reflection is not perfectly going to 1, but it's slightly smaller, because some amount of waves are actually leaking in. It's not a very strong band gap. Okay, very narrow band gap. And that's why the reflection is now smoother here. So you see, it's a very easy way you can understand and try to analyze for yourself. All right. I hope, you will take some time to try to understand these aspects. Okay, do try it out, see what happens. Change the angle of incidence of these structures and see what happens. So we'll share the T-matrix code. All you have to do is go and find the angle where the command where we set the angle, change the angle and run it. No harm. Okay, and you can try to analyze. You might even ask, okay, let's go forward and we'll come back again. So let me move to the next point that I want to highlight. Okay, so far what we have seen is a periodic structure, a perfect lattice. Let's say, the high and the low index. Let's say this is my high index and this is my low index. I'm just repeating it multiple times. But something interesting can happen when you actually introduce what is known as a defect state. A defect could be simply that a defect could be, this defect can be change in the thickness. One layer in the stack has larger thickness. Okay, has higher thickness. Okay, I don't want to write it. Basically, T increases, thickness increases, or no, we call it D, right? So let's say one of the layers has, in this case, this is my defect layer because it has higher thickness than the rest, higher D than the rest. Okay, so other stack is continuously having the same periodicity, but just one layer has a higher thickness. Or it could also happen that you can have a state or one layer has different epsilon. You could simply remove one of the layers. Okay, if you do that, again you can get a defect. So the way to think about it is, if I imagine the periodic structure as simply a lattice, it's a lattice, right? So it's having varying permittivity. So let me say I have a permittivity which is varying like this. So I have this periodic function. Okay, let's assume that all of that is uniform. But then in one structure here has a slightly one location, it is thicker than the rest, and the rest of them are same, identical. So the band gap exists in this structure right here. The band gap exists in both these places. But what happens at the layer which is thicker? Okay, so we actually draw parallels from the electronic transport theory, wherein if you have a defect in a lattice, we say that it creates a state in the band gap. Similarly, if you have a state like this, which is one location where there's a defect simply thicker or having a different epsilon from the rest of the layers. If you have such a scenario, you can have a defect, and that defect can occur within the band gap. Okay, so this is the defect state. Okay, you might say, when I say defect, it might feel like it's a negative connotation, it's bad, but no, it can be useful. So the reason is, this particular energy level is allowed, right? This particular frequency, is allowed to propagate. Where is it allowed to propagate? At the physical location of the defect. Okay, so we'll see that in the literature a lot of work has been done wherein they try to introduce, let's say, a defect. Of course, in a one-dimensional case that we are discussing right now, it's hard. But in the next lecture, we'll talk about the two-dimensional case, wherein we see that if you have a two-dimensional arrangement of this material, and in that one defect you can introduce and actually cut a path, let's say in L or whatever shape, you can actually confine the wave to go, make the wave to go in that particular direction which you have actually created the defect in. So you can actually have wave guiding through the defect states, and that's why it's very, very important. So we'll again, try to come back to it. Okay. So this is about the defect states. And one last point I want to mention before I conclude my discussion on the 1D photonic crystal is actually what is known as off-axis propagation. So far, the examples that I have shown, those are all cases where I have considered only normal incidence. Okay, even though my graphical schematic was looking like I have a wave here and reflection, but that's a generic case. But all the band structures that I have shown so far are for normal incidence. What do I mean by that? Well, I can simply assign a Cartesian coordinate system to this. So let's say this is Z and this is X, Y and Z, and I have in the negative Z direction the incidence. So when you have such a scenario, we've already discussed the band structure. What happens? So now electromagnetic wave is incident from the top. So you can have a X or Y, electric field in the X or Y directions. Okay. So for example, now your electric field can have two particular conditions. So you can have an electric field which is along this plane, right? Or you can have a situation where the electric field is perpendicular to the plane. But in effect, since you're normally incident, the wave does not see any difference. Because for example, the wave is able to go in this direction. So whether the electric field is here or here, it doesn't make any difference. It's going to feel the same environment. Okay. And that is why you'll see, if you look at the band structure, I don't know if you noticed previously, we are only now showing the half the band structure. Remember, when I talked about the band structure, I said that we are going to have minus pi by a to pi by a. Okay. And then you can show the band structure, right? Now I'm only showing the left half of it. So I'm only concentrating on the 0 to minus pi by a. So this is what I'm showing here. This is the on axis, or along the axis of the crystal, on axis incidence. When I have on axis incidence, you notice that in principle we introduce what is known as TM and TE modes that can exist as solutions to the electromagnetic waves, right? Solutions to the Maxwell's equations. So now when you have on axis incidence, you see that the modes that can exist here, modes are degenerate. Degenerate is a term we use to essentially say that the modes coincide. So you can't physically distinguish between a TE and a TM mode when you have on axis incidence. But interesting things can happen when you have incidence from off axis. Okay, what do you mean by off axis? Well, simply that I can have an electromagnetic wave incident from the left. Okay, so such a way that, let's say my wave vector is going to be some ky. It's confined to ky. Yeah. So it's basically incident from the left. So this is my axis, y axis. So along the y axis it's incident. So I have only a ky vector, and then there is no x and z components. I can have such a scenario as well. So that is called as off axis incidence. And when you have such a scenario, you'll notice that now the electric field can have one direction could be like this, out of plane, there's an electric field, or you can have an electric field which is perpendicular. This is E field. This is for off axis incidence. So now you see that the electromagnetic wave experiences different environments depending on whether you are in one of the directions. So TE and TM polarizations have different response, and that is why the band structure again becomes different here. So the blue represents the TM mode and the red represents the TE mode. So basically now we see that the degeneracy here, degeneracy is lifted. That means there is no more degeneracy. So the modes can occur at different frequencies, TE and TM modes. Okay, the same thing you would have studied in the electromagnetic wave propagation in various waveguides and so on. All right. Another interesting aspect is, you notice that if I have any random incidence, okay, not specified to one direction, it is nearly impossible to get a band gap, because you notice here, let me say if this is my structure here. So this was my original band gap in the normal incidence. There is no wave allowed. But then the moment I go to off axis illumination, I'm seeing that the waves are allowed. So to actually create a band gap, a so-called omnidirectional band gap, is a challenge, and people have looked at it. Okay. There are certain conditions if you satisfy, you can create omnidirectional band gaps even with single 1D structures, but it's challenging. All right. One of the ways to maybe do that would be to identify what is a light line. Light line is basically where it goes from 0 to 1. So this is my light line. So the modes on the right of the light line, essentially this n equal to 1, n equal to 2 modes, are guided modes in the structure. Okay, but we'll have to have as you saw in the case of surface plasmon polaritons, they need to be excited with specialized geometries. Anyway, so but yeah, the take-home message I want to give you at this point is that if you want to have reflection here, you saw the reflection spectrum here. It's nicely reflecting, highly reflecting, but it's only for normal incidence. If you come with off axis, you will see that the reflection spectrum is modified. And it turns out that if you come at any arbitrary axis of illumination, you will have reflection in one or the other place. So photonic band gaps cannot exist for arbitrary omnidirectional incidence. Okay. So we'll have to do some specialized things. In 1D, they cannot exist. Okay. So with that, I would like to stop my discussion on the 1D photonic crystals. All right. Thank you so much for your attention.